Hello, in this video we're going to be starting our adventures in relativity, a very fun and pretty wild field of physics where we talk about what the heck moving even means. Um, all right, so here's some ideas. This guy on the right here, is he moving side to side? I mean, probably, right? But not to these guys. He's just bouncing up and down. If he was moving side to side, it would be bad news, wouldn't it? Um, the idea is going to be that speed is really a relative thing. uh, More so than you might even think. Because, like, okay, well, this guy surely is at rest, right? Not moving? Well, I don't know. He's on the Earth, yeah? The Earth is moving 67,000 miles per hour around the sun because it careens through the solar system all the time. Okay, so maybe that's how fast he's really going. Well, the solar system is flying around the galaxy at something like 500,000 miles per hour. So how fast is anybody going? Well, the deal is it's all relative. So we're going to look at Galilean relativity, which is kind of an introductory, simplified version of relativity that works super well at low speeds. So let's get into it. So the thing we need to do whenever we're talking about like position, speed, really, is we always need a reference frame. It really doesn't mean anything to talk about a speed if you don't have a reference frame. And we're used to this, believe it or not. A reference frame is really just a coordinate plane. So it's just a regular XYZ plane. So whenever we're saying like this thing has a displacement of 5 meters, there's an implied reference frame. You're saying, in this XYZ coordinate system, it's moved 5 meters to like the right in the X direction or something. And the type of reference frame we're always working with is something called an inertial reference frame. The key thing is that the reference frame is not accelerating. Officially, an inertial reference frame is a frame in translational equilibrium, which remember means moving in a straight line at constant speed, which can include zero. And again, what does zero speed even mean? We need something else that to be relative to. Okay, but we are always working with not accelerating reference frames. If you want to work with accelerating reference frames, it gets very fun in general relativity, which is way beyond what we're going to get into. So if we have a moving reference frame, for example, like a moving bus or train moving past somebody standing at rest, the idea is that those are called inertial reference frames. And the assumption here is that Newton's laws of motion, our classic 3 laws, are the same in any inertial reference frame. So whether you're sitting, let's say, at rest on the ground and throwing a ball, or you're standing inside of a moving train and you throw a ball, all the ball will behave in all the same ways. And this is the idea. Inertial reference frames can move relative to each other. So you could be inside of your car or inside of a train versus standing on the sidewalk. Those would be 2 frames moving past each other is how we're going to define it. So if you're inside of the car, like where you're sitting might be your origin. But to somebody standing on the sidewalk, your origin is going flying past them. Yeah, so that's the idea with it's all relative. And we'll look at some examples to get into that. Okay, here's a few to kind of visualize. This is tricky to visualize, so do your best. But we have 2 sort of situations where we have different reference frames. So this is sort of a classic, and we do this a lot in relativity. It's a good problem where like you have a train or a truck or a car or something moving side to side and something happening inside of it, because that's a pretty digestible one, I guess. All right, so the bottom one is kind of if you're standing on the ground and you see this train going by, and inside of the train there's like a ball bouncing up and down. For why not? Sure. Right? You would, if you could like see through the train, you would see the ball like bouncing up and down and going side to side because it's moving with the train. But in the reference frame of the train, where we would say like, okay, let's just make the center of this car 0. Let's say like the origin is here, just for argument. Well, then the ball is just bouncing up and down, not moving horizontally at all, right? But the road is like moving backwards past us. So those are 2 different reference frames. I could measure things from inside of the train, or I could measure things from the ground. Both are saying the same thing. Both say the same thing happens to the ball, and that's really the key thing. It just depends on like where you set your 0 and whether your 0 is moving relative to some other 0. Over here is another kind of fun one. You got like a little frog or something happening. I got a boat moving across a stream. So these are some like logs going down the stream, very precarious boat ride here. But in the reference frame of the ground, so here's like the, shore, the ground, and there's two, I don't know, docks or something. I don't know what this boat is doing, but it's going side to side, back and forth, and you can see like the stream is flowing down. So we see the little logs on the stream flowing down. But what if you were on a log? What if you're sitting on a log watching this happen? Well, you would see the boat like move backwards past you, and it would look like this. Because to you, you're sitting on a log, you're at rest in your own reference frame. So this is what we mean by two reference frames. This will take certainly some practice and thinking to get a little used to, but do your best to try and think through this and wrap your head around and visualize this whole idea of reference frames. It's a really important one for all of relativity. Okay, so there are some simple equations that we're going to do for this introduction with Galilean relativity. Comes from good old Galileo, and in a lot of ways, these are based on Newton's assumptions of absolute time and absolute space. The idea that, time is the same for everybody. If I say 5 seconds passed for some event to happen, anybody else in the universe surely would agree that event took 5 seconds, regardless of moving reference frames, right? Right? I don't know. But for everyday situations, these are good assumptions. So we assume that like space is consistent everywhere. Time is consistent everywhere. We're going to break that all apart once we start going close to the speed of light. But for stuff like a ball on a train, this is perfectly good. And so here's sort of some of the notation we're going to use. You might see different things, different places. But a lot of times we use like S and S prime. You're always going to see this prime stuff, and the prime is usually, again, it's all relative, so this is where it gets a little tricky, but the prime we usually say is the frame moving relative to some other frame S, which we're going to treat as though it's like at rest, at least relative to S prime. Okay, so we can have like X, Y, and Z coordinates in two different reference frames, and we can relate them with this equation. So here's our first data booklet equation, which relates the position in two different reference frames where one is moving relative to the other. So we'll practice with this in a second because it makes more sense once you do some math with it and look at like an example. But essentially, if I have, let's say the S is the ground, so I can define like an event that happens relative to the ground that happens at like point X, point Y, takes a time like T, let's say. I could translate where does that happen on the train in X and Y. And this equation is what will do it. And it's a pretty simple equation. Here is a little picture to help visualize why it works. But the prime is going to represent the moving frame. X is going to represent the S frame, our kind of like standard or at rest frame. And V is the velocity of the S prime relative to S. So it's the velocity of the X prime stuff happening relative to the X stuff. So let's look over here a little bit and see if this helps. We can picture two different coordinate planes. And again, maybe picture kind of one of the more straightforward ones is the bus or the train and the ground. So let's say like the S frame is the ground and the S prime frame is the train, which is like moving. You might see this sometimes. This is, okay, WRTS, with respect to S is what that means. So this is how fast it's going with respect to the S frame. So it's moving at a certain speed. This would be like the speed of the train moving, measured as on the ground. So the idea is at time t equals 0, we're going to define that to be where the origins align, is typically how we're going to do it to keep it relatively simple. So at time t equals 0, like your 0 and the train 0 perfectly lined up, and then time ticks on from there is how we'll sort of measure this. So, well, after time t, the train's origin is like ahead of you now, yeah? Your origin's still here, but the train's moving, so its origin is there. So if you wanted to measure like where that ball was, you would say, okay, the ball like is way up here. Let's say that's where the ball is like bouncing, where we care about at time t. To S prime though, that distance is not nearly as big. So that's kind of where this equation comes. X prime, the position relative to the moving frame, is equal to X, the position relative to the original frame, minus this, which is really just the distance that S prime has moved relative to S. This might help, I think it makes a little more sense the other way if we solve it for X, just X. x would be x prime plus vt, and you will have to do this sometimes, depending on what you're solving for. So the x position would be my x prime, which is just this far. That's like, where the train says the ball is bouncing at the moment. And to find with the position in the S frame, the position relative to the ground, well, I would add this, right? Because this distance plus this distance gives me the distance measured in x. So that's all it's really doing. Again, we'll do some examples, and when you practice this, it'll start to make a little more sense. Okay, but that's the rule. We're just saying one thing's moving relative to the other, so we can figure out like where stuff happens and how long it takes relative to each reference frame. Okay, so let's look at one. We can do a problem like this. You have a cyclist riding a bicycle on a straight road. They move 480 meters in the reference frame of the road. The most important part with these is going to be keeping track of like our two reference frames. So one of them is the road reference frame. I think we'll probably call that S, but let's read the whole problem. Then there's a car moving at a constant velocity of 12 meters per second relative to the road that overtakes the cyclist. Calculate relative to the reference frame of the car. So to me, and again, this is all relative, and you can do it the other way, but to me, the car is moving like relative to the road. Let's say the road is S, the road reference frame is S, and the car reference frame is S prime. Okay. The tricky part with these is really digesting and like keeping track of the different variables, because your x prime versus x thing and v is going to be confusing. You really got to think about them. So we want to spell all that out. But all right, let's see how we want to start this. So I want to find first the displacement of the cyclist in 1 minute. How far does the cyclist go in 1 minute? Relative to the car. We know it moves 480 meters relative to the ground, but what about the car? So, I can kind of picture, I have my cyclist on my very beautiful bicycle here, right? Goes 480 meters along the ground. And that's in like a, reference frame relative to the ground. Then there's a car, right? Beautiful car that comes up behind it at some speed v, and the car is moving this way. And to the car, how far does the bike move relative to the car is really the question. Okay, so we can figure that out with that equation. Let's start with the equation. I'm thinking I'm going to use this equation because, well, I just gave it to you, so it seems like the thing to use. And I want to find displacement, which we can use displacement and position pretty interchangeably here, since we're just saying like x equals 0 happens when t equals 0. Okay, so I want to find the displacement of the cyclist in 1 minute. I know this 480 meters, and this is 480 meters in the reference frame of the road. That's in the S reference frame, so that makes this x. All right, the thing is, if you're like in the S reference frame, whoops, got S on the mind. If you're in the S reference frame, we're dealing with x, and if we're in the S prime reference frame, we're dealing with x prime. So that's really a way to think about it. This is in the road system, so it's just x. It's moving with a constant velocity of 12 meters per second. It is a velocity, so direction matters, and it's moving, it's overtaking the cyclist, so I know it's moving in the same direction as the bike is, and we're going to call all this positive. So I'm going to say v is positive 12 meters per second. I put the 12 in here, and I know time is 1 minute. And of course, we're going to want to make that 60 seconds. Okay, so what am I really solving for? Well, it's the thing I don't have, the displacement of the cyclist in the reference frame of the car, which is x prime. So we're already kind of solved for what we need. All right, so let's put in these numbers and see if this makes any sense. We're going to do x prime, what we want, is just going to be equal to x, the 480 meter distance traveled by the car, minus the speed of the car's reference frame relative to the road's reference frame, which is 12 meters per second, times 60 seconds, the time. Okay, so I put that in my calculator, 480 minus 12 times 60, and I get a negative answer, negative 240 meters. Okay, that negative matters a lot. The negative really means something. So let's think about what this means. I'm figuring out, in terms of the car, what's the displacement of the bike? Well, negative must mean like, backwards, this way. And I think that makes sense. If the car is overtaking the cyclist, this seems like we got the right answer, because to the car, if you're sitting in the car, all this means is the bike moves backwards relative to you. Yeah, so like for example, maybe in this 1 minute you overtake the bike, right? So maybe it started 120 meters ahead of you, and after 1 minute it's 120 meters behind you, right? Doesn't mean the bike, like to the bicyclist, is moving backwards, but to you in the car, the bike has displaced 240 meters backwards. That's what we're saying. All right, and this equation is just like a simple way to do that. Okay, so the bike moves backwards relative to the car. Makes sense. Let's find the average velocity of the cyclist. Well, this one's pretty easy now that we know this. Just remember how we do average velocity. It's total displacement over total time. Now, which displacement will I use? Well, I'm still talking in the reference frame of the car. So how fast is the bike going? Well, what's its total displacement? It's negative 240 meters. And the time is 60 seconds. So that's all we're going to do. We're doing average V is the total displacement over the time. And I get negative 4 meters per second. Again, the negative is meaningful. So if you're sitting in the car, to you, the bike is getting closer to you by 4 meters every second. That's what it means. Makes sense since we're overtaking the car. All right, so that's how you do these relativity problems. That's the idea. It's really about keeping the, what reference frame you're in straight. Sketching helps make a beautiful sketch like I did. Sketching and thinking about your two different reference frames and your x primes versus your x's is the main thing, which will take some practice. Let's look at a couple more things that you can do, because we can also deal with velocity. Just like position is related to moving reference frames, so is velocity. So you can do velocity addition. The idea being like, say you're sitting in the car, you're driving your car at like 50 miles an hour or something, and somebody in the passenger seat, don't try this at home, but like, takes a baseball and throws a fastball out the window. And like to them, they throw the fastball, I don't know, let's say 70 miles an hour. How fast would it be going to somebody on the ground? Pretty fast, right? I'm thinking like 120, something like that. You add them up. All right, the velocities essentially add when you're dealing with these moving reference frames. So, here's a girl on a sled throwing a snowball at 1.5 meters per second, being towed at a speed of 1 meter per second. So to this poor kid, the snowball hits him at 2.5 meters per second, because those velocities will add together. Whereas over here, even though the snowball is being thrown at a speed of 1.5 meters per second, and we're moving the whole system 1 meter per second this way, this guy, the snowball is moving away, yeah, but not quite that fast, right? Okay, so essentially the velocities just add up, which, give it some thought. It'll make a little sense as you picture these things. But this is all you do. You basically add / subtract depending on what you're dealing with. So again, prime is like the moving frame. So pictured pretty well here. I think this picture is a really good one to highlight what we're talking about. So U prime is the speed in the moving frame, because this whole frame is like moving relative to the ground. So we would typically call, the observer, kid on the ground here, is the S frame. Moving sled system is the S prime frame. So the snowball is going 1.5 meters per second in the prime frame. I would take off this V, I guess, to find the speed in the from the speed in the S frame. All right, so that's how those three things are related. There's also an equation in the data booklet, which is kind of hilarious, but there it is. That's the assumption of absolute time. The time it takes for the snowball to hit this kid is the same for the person in the moving sled to the observer, right? Makes total sense. That's how time should work, yeah? If like the girl throws a snowball and it takes 2 seconds to hit the boy, I would expect the boy to measure the same 2-second time that it takes the snowball to hit, right? You would think that's always true. It seems like so simple. Right, but it does work at low speeds. Okay, so there's your things again. We're talking about like a moving object in two different frames of reference. U prime is in the kind of moving frame of reference. U is in the stationary frame of reference. V is the speed of the moving frame relative to the stationary frame. Again, all relative stuff. T is your time between events, and the time between the events should be the same in the two frames, said Newton and Galileo. All right. All right, let's look at one more with that velocity addition stuff to show one more type of how you do these. Okay, now I got a bus, classic. A bus is moving and somebody's walking on the bus. So a bus moves at a constant velocity of 8 meters per second. Passenger on the bus walks towards the rear of the bus at a constant speed of 1.5 meters per second. So again, a picture very helpful, and it doesn't need to be very, beautiful. There's my bus. My bus is moving at 8 meters per second, and the person on the bus is moving towards the rear of the bus. That's going to be important. So the person is going like this way, yeah, at 1.5 meters per second. Okay. Let's decide how we want to define this stuff. I'm thinking, and we're going to do relative to the ground. I'm thinking we'll stick with S as the ground and S prime as the bus. You can do these backwards. You can say S is the bus and S prime is the ground. Again, it really is relative and it really doesn't matter. The trick is if you did it that way, you would have to say V would be that the ground is moving past the bus at like -8 meters per second, because the ground would be moving backwards relative to the bus, so that part gets a little weird. But you could do it, but let's stick with this. The ground is S, the bus is S prime, it's moving. That makes this the V, and it's moving forwards in our reference frame, so we're going to call that +8 meters per second. I have then also this, the speed of the person in the frame of the bus, right? This is relative to the bus. They're moving 1.5 meters per second, like backwards. So that's going to be U prime, because that's the speed of the object in the S prime reference frame. And I want to find the speed in the S reference frame. So I'm trying to solve for U. Okay, so honestly, like everything in physics, this really comes down to knowing your equation and knowing what the variables are. The variables here are kind of tricky because it's like speed in one frame versus speed in the other frame and just keeping your frame straight. But that's the main thing. Because the equation is very simple, yeah? The equation is just U prime equals U minus V. You just got to know what U is what and which one you're solving for. And here I think we're solving for U. Oops, that's a minus. Okay, here we're solving for U. So I need to add V to both sides. All right, this is the main like tricky part. Again, it's like what am I looking for, and use the math to tell you from there. Okay, so this is U. All right, so I just add the U prime to the U. And I think this will be very intuitive. It's probably what you would expect. The speed relative to the ground would be the speed relative to the bus, which is -1.5. These are vectors, so that matters. So that's U prime meters per second, plus the speed of the frame, which is 8 meters per second. So what did I get? 6.5 meters per second. Okay, it makes sense. If you're standing on the ground here, right, watching the bus go by, the bus is moving 8 meters per second, but this person is moving backwards 1.5 meters per second, so like not moving as fast, yeah? Imagine if this person was moving backwards at 8 meters per second. What would you see? They would be at rest, no? Crazy. Okay. The distance walked by the passenger relative to the bus is 3 meters, and I want to find the distance during the same time relative to the ground, so I'm thinking this is going to be the other equation that we looked at because I'm dealing with distances now. So it's a distance walked relative to the bus is 3 meters. I know my equation needs a displacement, and this is on the bus, so it's my x prime. So I'm going to make that again -3 meters because they're moving backwards on the bus. Calculate the distance traveled relative to the ground, so I'm trying to solve for x. And all right, so I know what equation I'm going to use because I also know I have the v, the speed of the bus frame relative to the ground frame. So I'm going to use this good old x prime equals x minus vt. Well, these are vectors. Now, okay, I know x prime, I know v, I want to find x. What that means is I need t, and t is pretty easy. We can be kind of sloppy and simple here because this person walks 3 meters. They're going at a speed of 1.5 meters per second, a constant speed, so I can just divide them. I'm thinking that's going to be 2 seconds, right? They're moving 1.5 meters per second, and they move 3 meters. That took them 2 seconds. And I just divide them. So there we go. Now I got what I need. I want to solve for x. So again, be careful what you're looking for. I don't this is the one I'm finding, so I got to move the VT to the other side. So x, the distance on the ground, will be the distance relative to the bus plus, essentially, this is the distance traveled by the bus, right, in that 2 seconds. That's the idea. So, all right, x prime is -3 meters because they went backwards 3 meters on the bus, but the bus went forward 8 meters per second times 2 seconds, so 16. So what's that? 16 minus 3 is 13 meters. That's how far they went, right? The bus went 16 meters forward, but to you standing on the ground, you saw this person went only 13 meters forward because they moved backwards 3 meters. That's really it, and that's what these equations all account for. All right, so that's the introduction. Things will get very fun when we start moving fast, but it's going to be the same idea of like 2 different reference frames and keeping reference frames straight and primes versus not primes. So that's the thing that takes some practice and is so fun. So I will leave you to do some practice and have fun.